Okay. So today what I want to do is go through chapter 4, the review of acids and bases. And then I have Wednesday scheduled for questions for the exam. Although if you have them, you should probably ask them maybe before Wednesday. But that's our plan, and then Friday will be the exam. I put online the sheet that I handed out last week that has the topics, and then I also put online for this acid base. Well, I didn't put online, I just linked up a video where it's just kind of what are conjugate acids and bases, which we'll kind of do today as well. So let's kind of go back to Friday and the last thing that we ended with. Because technically you're not supposed to end on a new topic, but I did. And that's the idea that if we have our generic equation for an acid-base equilibrium, just an acid dissociating into H plus and A minus. So if we have this, then how can we push this? What factors can we use to push the equilibrium to the right to make a stronger acid or to make maybe a weaker acid? And then what effect would that have on the conjugate base? So what we said was that anything I can do to make the conjugate base more stable is going to push the equilibrium to the right and make HA a stronger acid. Okay. So anything I can do to make it more stable, that's what's going to make it a stronger acid. And that's what we're going to do 6 different ways today. We're going to make the conjugate base more stable so that that acid becomes stronger. Right? Okay, so that's the basic principle. How you do that could be a number of different ways. So here's So I have a whole bunch, instead of doing this kind of as an icebreaker and letting you guys work on these problems, we'll do them one at a time. So I will send them out one at a time. Okay. And the first thing is that there is this thing called Ka. If I go back to this equilibrium, Ka is the equilibrium constant for that acidity equilibrium. Okay, so first question. The first question is going to be this word problem. The blank the Ka of an acid, the blank the pKa, and the blank its strength as an acid. So you get to match up the terms with those. Okay, let's see what your responses were. I think. Okay. So, what did we have as our responses? So, the first blank, the larger the Ka value, and this actually, there's probably, you could do this either starting out with the larger the Ka value or the smaller the Ka value, because you could do it completely opposite. So we'll start with the larger, since that's what most people did. So the larger the Ka value, the smaller the pKa. Because remember, the pKa is what? It's minus the log of Ka. Remember the pH scale. What's a stronger acid? 7 or 4? Which is a stronger acidic solution? One with a pH of 7 or one with a pH of 4? The pH 4. So Ka goes up, pKa goes down. And then for the third blank, the stronger its strength as an acid. So you could have also said the smaller the Ka, the larger the pKa, and the weaker the acid. But our key thing here is we're going to be dealing in pKa's, so the smaller the pKa, the stronger it is as an acid. Okay? Because you're going to match up some acids with pKa values for multiple choice, or kind of matching, and so that's what you have to remember. The stronger the acid, the smaller the pKa. Okay? So, good. We remember that, or we remember it from the reading. All right. Question number 2 about conjugate acids and bases. So I've got 2 equilibria here. I have an acid equilibria on top and a base equilibrium on the bottom. And the question is matching up the terms. So what is the acid? What's the base? What's the conjugate acid? What's the conjugate base? Okay. So we want to match those terms up. And we're going here we're going to go from the perspective of left to right. Not the reverse reaction, but from left to right, the forward reaction for each of these. Push. Okay, last couple people. Okay, let's see what we've got. All right, so we have the acid as number 1, the base as number 3, the conjugate base as number 2, and the conjugate acid as number 4. Okay. But those second 2 numbers drop off a little bit. So the acid always produces its conjugate okay, let me go back to the hat. So if I have my HA going to H plus and A minus, this A minus is always going to be the conjugate base. And the way I like to say it that kind of helps me, if I said, hey, what's the conjugate base or the conjugate acid of a species? I like to say this is the conjugate base of the acid HA. So that if you know it's the acid HA, then you know to make it its conjugate base, you should do what? If you want to change the acid into its conjugate base, what do you need to do? Okay. Here's H2CO3, carbonic acid. What's its conjugate base? So what's the conjugate base of the acid carbonic acid? HCO3 minus. So what did you do? You lost a proton. So when we say it's a conjugate base of the acid, then we know it's acting as an acid. We lose the H plus to get us the conjugate base. If I said, what's the conjugate acid of Cl minus? What would you say? HCl. The conjugate acid of the base, Cl minus. So in that case, what do? You add a proton on. Okay. So when we're looking at acid-base equilibria, we first have to identify, is it acidic or is it basic? Is it an acid reacting or is it a base reacting? And then the other species on the other side, that is the conjugate acid and the conjugate base. All right. Does that make sense to everybody? You're going to get the opportunity to do that again shortly. Okay, if there's anything that doesn't make sense, but I just went through yesterday and thought, okay, we'll just do these questions one at a time and see how good everybody's doing or how not good everybody's doing. Okay, equilibrium term matching, what's that? Oh. How can we already have responses? Did I click it? Oh, it's sent to out. So did everybody here, I'll send. Maybe I can let you answer this one. Nope, go ahead and answer this one. If you answered it before, I guess you're locked in. But okay. Now, what's the first thing we have to do for this reaction?
Figure out which one's the acid and which one's the base.
Got to determine which one's the acid and the base. So in this case, which one's the acid?
That H2SO4.
Because it's donating a proton to the HCO3 so that it becomes HSO4 minus and H2CO3. So that's the first thing you have to do. That may seem obvious, but that's the first step. So then we know number 1 is the acid. We know number 2 is the Roman numeral 2 is the base. Good. And then number 3 is the conjugate base of the acid H2SO4, and 4 is the conjugate base. Okay. So that looks good. Second time through, we got these two numbers look good. So that tells me on a whole you're getting it, or you got it for that problem. You just want to make sure you continue to get it whenever we have a test. Okay, everybody okay with that? All right, so we're just going through the basics. So they'll get a little bit more difficult here. Wish this would just stay in chapter 4, but it won't. Okay, periodic table acidity trends. So here is the periodic table. And which of the statements is true? And you can click all of the ones that are true. Okay. And obviously there's two sets of questions, so one of the first two has to be correct and one of the second two has to be correct. So, looks like we have a majority of people saying moving left to right horizontally, the acidity increases. But then we have a little more than 50% saying moving down the column has the acidity increase. So as we go left to right, acidity increases. As we go down the periodic table, acidity increases. And let's use this as an example. We've got fluorine, chlorine, bromine, iodine. What's the difference between HF and HCl? If you can remember from general chemistry.
HCl fully.
Okay, HCl fully dissociates in water to form H plus and Cl minus. I know it's supposed to be H3O plus, but and then HF is involved in an equilibrium to form H plus and F minus. So it only partially dissociates. And if you were to go back and look at your notes from general chemistry, you would probably see that you did a lot of ice charts. Remember initial, change, equilibrium, that you did a lot of ice charts with HF. So HF then is only partially dissociated. That makes it a weak acid. HCl completely dissociate. That makes it a strong acid. And then as we go down the periodic table, HBr and HI are even more acidic. Now you might say, how can HCl dissociate less than 100%, or how does HBr dissociate more if they're completely dissociated? They're not completely dissociated. There are small differences between HCl, HBr, and HI. HI is more dissociated in water, but in general chemistry we usually just say, okay, it's completely dissociated. But there are some differences. And actually they're not completely dissociated. But it works well in general chem. So as you go down the periodic table then, HI would be stronger than HBr, stronger than HCl. As you go across the periodic table, HF is partially dissociated in water. Of course, the oxygen would be either water, which is partially dissociated in water. But when we go to something like nitrogen, if you put a nitrogen compound in water, what happens? It doesn't dissociate to form H plus. It grabs a proton to form OH minus. And carbon doesn't do anything in water. It doesn't dissociate. So our acid-base strength is acid strength this way, acid strength that way. And now realize that I could change this question up and say, which way does basicity go? And if I said which way does basicity go, then you would go in the opposite directions. Or I could even say, what's a stronger base? C minus or O minus? C minus? Do we all agree on that? So C minus is stronger than O minus because I'm going now in the opposite direction. The oxygen is a stronger acid, and therefore it's going to have the oxygen OH compared to CH, OH compared to CH, this is a stronger acid, which means it has a weaker conjugate base. So the O minus versus the C minus, that's now stronger. So there's also a relationship between acid strength and conjugate base strength. The stronger the acid, the conjugate base. The stronger the acid, the weaker the conjugate base. Okay. And a lot of times all we have is a table of acidity. We don't have a table of basicity. So, I mean, this is the most difficult part of acid-base chemistry, is all these inverse relationships. Because by the time you invert it like 4 times, you're back where you started from. So you have to keep those in mind. And if I would have been smart, I would have put that question on there and said, the stronger the acid, the weaker the conjugate base, and vice versa. Okay. Still okay? Okay. And these reactions that we've been doing, if you want to push the equilibrium, which of the statements is true? And there's only one that's true. Okay. The majority say the equilibrium is pushed towards the side with the weakest acid-base pair. So whenever we look at an equilibrium, we're always going to have the strongest acid with the strongest base, and then on the other side, the weaker acid and the weaker base. Could be either way, but they're always together. And so it always pushes towards the weakest side. It's basically reverse tug of war. The strong side always pushes towards the weak side. So that means when you're evaluating an equilibrium, you just have, if you know, you have to find 2 acids and say, okay, which one of these 2 acids is stronger? Or find the bases and say which one of these 2 bases is stronger. And a lot of times you'll have to use a chart for that. And so if I asked you to do that, I'd have to have a chart of acids and acid strength. Because once you have the acid strength, you automatically have the base strength in the reverse. Okay, good. So next. All right, let's use our new friend, the pKa. So here's an equilibrium. Where does the equilibrium lie in this case? To the left, to the right, or is it split down the middle? Okay, let's see what this one looks like. Okay, equilibrium's pushed to the right. Why? Somebody step me through their logic.
So on the left side, the pK value is smaller, so that means the stronger acid, and so equilibrium shifts towards the side that's weaker, so it shifts right.
Okay, so pKa, the stronger acid has the what kind of pKa? The lower one. So have I identified both of the acids here? Yes. The going from left to right, the carboxylic acid is protonating or giving up its proton to the NH3. So NH3 is the base, carboxylic acid is the acid. But in the reverse reaction, it would be the ammonium that's the acid, and the carboxylate, the deprotonated carboxylic acid, would be the base. So we have to find the pKa's of both acids, and that'll tell us which way the equilibrium is shifted. Okay. Next. Okay, so for this one we have acetic acids where I have three groups attached to the CH2. A hydrogen, a chlorine, and a fluorine. And I have three pKa's listed. So you have to match the structure with the pKa. My hint here is that as we go through this, we're now going to end up in that basic first principle that I talked about at the beginning of class. How do you push the equilibrium to the right? Okay, one more. All right, responses. So, which one did we think is the strongest acid? Why am I... Let me go back here. Oh, that's not good. That's okay. So we have 14% correct. Right. So really, I'm asking you which one's the strongest and which one's the weakest. So which one did you think is the strongest? When there's an H, a Cl, or an F attached. Cl? What else? What everybody else think? Strongest one. Lexi? Right.
Yeah.
Katie?
Yeah. Yeah.
Okay. Everybody else over here with Cl2 mostly? F? How many people said F? Actually, sit down this way. How many people said F? You said F. Raise your hand. Cl. H. Okay, so it's between F and Cl. Okay. So, here's I've got a CH2 attached to a group with my C double bond O with my OH, and that's going to dissociate to form the conjugate base. And my H plus. Okay, so how am I going to push this equilibrium to the right? In other words, which molecule is going to have the most stable conjugate base? And everybody said Cl, right? Except one. Or most people said Cl. How's the Cl stabilizing the conjugate base? No.
Increases in size, so it's better to collect
Size isn't... Well, we're going to compare to fluorine in a minute. But size isn't necessarily what isn't the property that I would focus on. If I put a chlorine there, what is its charge? What's the charge on the chlorine?
Negative.
What kind of negative? Partial negative. So the chlorine's delta minus. What's the carbon in the CH2's charge? Thank you. Partial positive. How did the chlorine become delta negative? By making the carbon delta positive, by taking away its electron density. So what? What can that delta positive carbon now do with the negatively charged carboxylate? So now we have this carboxylate that's negatively charged. If this is slightly positive, then what can happen is it can begin to suck some of the electron density out of the -1 And that's actually going to make it more stable. So I want to reduce the negative charge. I want to, better term, I want to spread out the negative charge. I want to delocalize it. And the more I can do that, the more stable the conjugate base will be. Okay. Does that make sense to everybody? So the chlorine's going to be able to do that because it's pulling the electron density out of the carboxylate. Are we all agreed that that's the case?
You saw the chlorine takes the negative charge.
So the chlorine's taking some of the negative charge from the carboxylate. So when I'm spreading out the charge, I'm spreading it from just the 2 oxygens on the carboxylate because remember it has two resonance structures, so it would look like this with delta minuses. But with carboxylates, what I want to do is I want to pull that electron density out and I want to spread it throughout the molecule. And chlorine's able to do that. Okay. Does that make sense to everybody? But Aisha, what's even better than chlorine? Fluorine is more electronegative, so the fluorine is going to do an even better job of pulling out that electron density. So when we are comparing the chlorine and the fluorine is actually going to be the strongest acid because it stabilizes the conjugate base the most. And then chlorine next, and then hydrogen, because hydrogen doesn't stabilize it at all. So if we go back to that problem then, the acid with the lowest pKa should be the one with the fluorine, then chlorine, then hydrogen. So this is what's called an inductive effect. The electronegative atom is able to stabilize the base because it's pulling the electron density away from the carboxylate. Right. So then, that principle is going to be the same. That principle is going to be the same, let's say, for these alcohols. So if I'm looking at these 3 alcohols, I'm going to have to figure out a way to take that O- in the conjugate base and spread it out. Okay, so let's see what we've got here. Okay, so we've got C being the strongest acid from 21 out of 29, using the same principle that we just used. So then what would be the next strongest, or what would be the weakest acid? And we're kind of split between A and B. Okay. Now in this case, what we should, what? Which one do you think is the weakest acid?
I thought it was
B?
Yeah.
Or A? B? How many people said it was B? A? Don't know? Okay, at least one. Probably more. I would want to draw my diagram out with my O minus. And then I want to go back and I want to remember, what's an alkyl group do? Carbon becomes slightly negative, correct? And hydrogen becomes slightly positive. And that alkyl group can do what? It can push electron density. Do you want to push electron density into a carbon that has a negative charge on the other side? I'm trying to delocalize the O minus throughout the molecule, and yet these alkyl groups are pushing negative charge the other way. Is that going to stabilize it? No. Okay. Well, here's what I'm going to do. I'm going to figure out how to get these remaining questions that I have into chapter 4. That could take me anywhere from 5 minutes to the rest of the day. But I will do that and I'll send you an email, and what I'd like you to do is to go in the chapter and answer these questions, and then I will I'll take a quick look. I'll probably end up recording a video over each one to show what was going on. So that way, if we don't, then I can do it on Wednesday. But on Wednesday, bring your questions. Or bring your questions earlier than that.
1 through 3 will be on the exam.
Is 1 through 3 going to be on the exam? Chapters 1 through 3 will definitely be on the exam.
No 4.
So, well, yes, no 4. But don't tell the afternoon people that, because then they won't pay any attention.
Wait, did you say 4 is not on the exam?
No, 4. It'll just be 1 through 3.
Oh.
We got plenty of stuff on 1 through 3.
All right.
Have a good day.
You too.